I would like to extend a warm welcome then as well. And I guess we'll now be switching to the main topic of today's training, which is LEAP. So I'm going to go and give you an overview of LEAP. We've heard already quite a little bit about people are using it already, and we're all here to learn about it. But what is LEAP? LEAP is a software tool for quantitative modeling of primarily energy systems. That's what it was developed to do, but also pollutant emissions from energy and non-energy sources, costs and benefits, health impacts, sustainable development indicators, and related externalities. And it is created by SEI to really support sustainable development, inform decision makers, and empower stakeholders to perform their own analysis. So the idea of LEAP is that it responds to the needs of users. It has around 10,000 of users around the world. And on one side, it is aimed at analysts and full-time modelers, but it's also aimed at stakeholders who are not modelers, but who have an important role in decision making. And so one of our goals with LEAP is really to make it very user-friendly and it doesn't require programming background. And so that's really meant to allow a variety of users to engage with LEAP and use it for their analysis. Often we hear LEAP does this or LEAP does that, but I would just like you to bear in mind that LEAP is in fact not a model. It's a tool for creating models. And with that, it requires that the modeler, as they develop their model, as you develop your model, you really make choices as you set up the modeling environment to represent your system. LEAP is well suited to a medium and long-term planning horizon. Usually we're talking about 20 to 50 years. Is not really useful in a modeling short-term horizons, the next year or days even. It facilitates data management and documentation throughout LEAP. There are many places where you can insert notes and document the model as you're building it. And the goal of that is really to enable other modelers, but also yourself, to keep track exactly of what you're placing in the model. And it also enables communication with stakeholders. Because of the documentation, it becomes easily accessible to stakeholders that use the model once it's developed. And you can use the variety of visualization tools that are really quite powerful in LEAP to visualize results from the model. So sometimes people will ask, well, so what distinguishes LEAP from other energy systems models, maybe TIMES? And here we've compiled a list of key characteristics that we think are quite unique to LEAP. One is that it has extremely broad scope and flexible data structures. It's capable, you can build a model with LEAP really in a very data scarce environment. And then as you proceed in developing your model and collecting data, you can add more detail and extend the specificity of your model. It supports multiple modeling methodologies. We really do not want to be prescriptive in the methods used. And the user can select these modeling methods, and all the modeling methods that are selected by the user are embedded in an accounting framework that counts emissions, energy, costs, natural resources. And so often people will say, in fact, when you look at the peer-reviewed literature, there is an overview of different energy systems models. This is where LEAP will often be listed, is among the accounting tools. But LEAP can do a lot more than that. It allows you to embed simulation and optimization methods within. And so, yes, it is developed as an accounting tool, but it is really much more than that. LEAP is also scenario-based, so it's really ideal to be used to evaluate the impact of different policies, assumptions, analytical questions, and compare them. And so here on the right, for example, you've got a visualization of some output, and the bars that are white indicate an avoided cost versus the reference case. So we often use LEAP to compare future scenarios, or often climate mitigation pathways, to a reference scenario that essentially implies that no changes are made with the particular goal in mind, which may be emission reductions. LEAP has a very powerful graphical user interface and visualization. So it allows users to easily access the software without having to program. And it also allows you to visualize the results of your modeling right within LEAP. And any visualizations that are produced can be exported easily. It's suitable for modeling at various scales. In the large majority of cases, LEAP is used to develop models at the national scale. But LEAP has also been used for subnational modeling, even at the city scale, as well as regional modeling across multiple countries and even global modeling. LEAP comes with a variety of default data covering conversion units, the physical characteristics of pollutants and fuels, and emission factors. And the goal of this is really to facilitate that users get up their models up and running very easily. Any of these characteristics can be changed by the users, but it's really easy to start out with a relatively limited data set and use some of the default data to make your model work. And then LEAP is most often used with an annual time step, but it does have the capability to also model seasonal and time of day details. It is integrated with Microsoft Office. Throughout LEAP, you will see here, I think you should be able to see my cursor. You will often see Excel and PowerPoint icons, and these allow you to export data from LEAP into Microsoft Office. And LEAP is widely used for energy planning, national communications, nationally determined contributions to the Paris Agreement, low emission development strategies, and air pollution action plans. So here I'm just giving you a little bit of a history of the tool and some graphics of our current user base in the bottom. Originally, LEAP was developed as a mainframe tool in the early 1980s. And in the mid-1980s, it was moved to Microsoft DOS, then existed as a PC version. In 2006, we developed an application programming interface that allows you to link LEAP to other models via its API. And only recently, last year in 2020, we published a major new version that includes advanced optimization modeling, results mapping using its GIS capability, as well as enhancement to the integrated benefits calculator, which allows you to assess the impacts of air pollution, indoor and outdoor, on public health. Currently, LEAP has a little more than 50,000 users globally, of which a significant portion is located in Southeast Asia. Just about 18% of its user base is located in Southeast Asian countries. And we have a variety of people from a variety of backgrounds use LEAP. We have students, but many academic organizations, governmental organizations, as well as private companies and nonprofit organizations are using LEAP for energy systems modeling. And so you can see that we have 4 decades of development and implementation with LEAP. A lot of you may already know this since we ask you to do this for this workshop, but LEAP can be accessed via the LEAP website, leap.sei.org. When you first download LEAP, you have a read-only version, and it requires a license to be fully activated. A license can be also accessed on the LEAP website. We have a tiered system of license costs. Licenses for LEAP are free for all students, as well as free for nonprofit, academic, governmental, and governmental institutions of low and lower middle income countries, many of which are present here today, with the exception of Thailand, which falls under the upper middle income countries and requires a nominal cost. And then we have full cost licenses for all other for-profit and high-income countries. And the idea here is that we really want to provide free licenses in places where there is not a lot of resources to get software. And we use the licenses from for-profit users in high-income countries to subsidize this use, because we want to enable as many users as possible around the world to use LEAP to develop their energy systems modeling. Once you set up a user, you can see on the website, you can see the types of licenses that you qualify for. It is very easy to apply for a license. You just have to click a button and someone will respond to you with a license. And we also provide technical support which is available through the LEAP website. And I just want to switch quickly and show you where you can find this, because I think if you come to use LEAP, this will be very useful for you. And so here under the Discuss button, can everyone still see that? Wonderful. You can click on LEAP support and you can generate a question. And we have really quite an active user base that uses the support forum, but also we at SEI monitor this forum and answer questions as needed. So this is a great resource as you are using LEAP if you have any further questions or run into problems. The installation of LEAP requires Windows. Unfortunately, it is not supported on Mac, Linux, or Unix, so you can have LEAP installed if you have a virtual environment that runs Windows. It requires at least 4 gigabytes of RAM as well as 1 gigabyte of free disk space, so the system requirements are really rather minimal and allow you to run LEAP on any laptop. Of course, if you do have more space available, LEAP in particular when you develop more complicated models in LEAP, that can be very useful to make LEAP run faster, but the minimal system requirements are really quite low, so anyone should be easily able to run LEAP. It does require administrator rights for installation, so you need to be logged on as an administrator or have your administrator install LEAP for you on your computer. And after we've talked so much about the general prerequisites, I want to kind of switch gears and look at the nominal structure of some of the components that could be included in a LEAP analysis. So this is a diagram. Originally, LEAP was built as an energy systems model. And so in the middle of this graphic, you really see the backbone of LEAP. LEAP models final energy demand, which is often premised on exogenous demographics and macroeconomics. And the supply side will then respond to the final energy demands that are modeled this way. LEAP also models the transformation from one form of energy to another, the extraction of primary resources, as well as there is a special module for land use change. It also includes statistical differences in stock changes, which are accounting conventions used in energy balances. For example, the differences between the final energy demand and the supply of fuels for final energy demands. But in addition to this backbone, LEAP has many other capabilities. You can model pollutant emissions. And this is often used to model greenhouse gas emissions, but can really be used to model any pollutant. You could model water pollution emissions. You could, many people use LEAP to model air pollutant emissions. You also have in LEAP an integrated cost benefit analysis. This allows you to, as you track the costs of different technologies in your model, you can track those where those costs are incurred and where benefits are incurred, and allows you to carry out an integrated cost benefit analysis. LEAP also has an integrated benefits calculator, which allows you to assess the impact of air pollution on mortality, crop losses, and temperature change. And then most recently, we have started to develop various ways of assessing the impact of different climate mitigation pathways on sustainable development indicators. This includes access to energy, but it may also go as far as assessing impacts on gender, in particular if linking a macroeconomic model. So there are many more possibilities than just the pure energy systems analysis. Typical inputs for LEAP include demographic and macroeconomic data and projections that drive energy demands. I may point out that this is a list of typical inputs. Not all of these, or in fact, only few of these inputs are required to set up a LEAP analysis. But these are some of the inputs that are typically used as you go and develop a model in LEAP. Detailed energy balances, surveys, and audits are used. Greenhouse gas inventories are often used to add activity data, emission factors, and emission totals. You may use grid operator reports to add the capacity installed, performance data, and cost data of different infrastructure. You then may also use natural resource reserves and potentials, plans and policies on energy, climate, air pollution, as well as the costs of equipment, capital, operation and maintenance, fuels, other consumables, as well as policy implementation. And here on the right, I'm just showing some examples of policy reports that have used LEAP to develop their analysis. Some of the typical outputs of LEAP include energy demand and supply, domestic production as well as imports and exports, pollutant emissions, direct and indirect, ranging from greenhouse gas emissions to air pollutants, for example, social costs, which can be reported both in real and in discounted terms for the baseline or reference scenario, as well as the different policy scenarios you are trying to assess. It allows you to produce energy balances and Sankey diagrams, which you can see on the right here. Then equipment capacity, stocks and utilization, natural resource exploitation, impacts of air pollution on public health and mortality, decomposition analyses, marginal abatement cost curves, and other user-defined indicators. And so the user-defined indicators are just another capability of LEAP where users are able to add their own outputs to a LEAP model, which are then calculated at runtime, and the results can be used to report on them. LEAP is intended as a medium to long-term modeling tool. Most of its calculations occur on an annual time step. In principle, the modeling horizon can extend for an unlimited number of years, but most studies really focus on the next 20 to 50 years. In particular, recently, we've seen a lot of nationally determined contribution reports that have looked at climate mitigation pathways looking out to 2050, but we've also done some analyses that go further out into the future. It generally allows you as well, though, to calculate energy demand and supply with a finer level of temporal detail. Years can be split into user-defined time slices. These may represent seasons, types of days, or times of day even, up to an hourly resolution. And this really allows you to explore some of the optimization capabilities of LEAP, for example. And so you can extend the default annual time step really to represent your energy system as accurately and realistically as possible. Demand is in this situation then determined by time slice, and supply is dispatched by time slice in order to meet the demand. And so you can then use this capability to really find solutions that will meet the demand at a much finer resolution than just annual. Time slices can be really easily reconfigured in LEAP to explore the impacts of temporal resolution on results. So once you've inputted your data at an hourly scale, you can easily change it to a seasonal or monthly time scale and explore what the impacts on your results of setting this time slicing is. And so that's a very useful tool within LEAP. LEAP has a variety of user interfaces, which show up on the left side of your LEAP model. So just going to pull up a LEAP version. This is the Fredonia model, which we are also going to use throughout the exercises. So here in areas, you can install an area, and so you can select Fredonia. You open the area, you select Fredonia, and that allows you to look at this. So if you have already installed LEAP on your machine, you can even follow me along. But what I just showed you on the slide is the overview here on the left side. So I'm now in the analysis view. And analysis is where you enter or view input data, you construct your model in your different scenarios. Then LEAP also has a results view, which is where you examine the outcomes of your scenarios, and you can look at them as graphs, bar charts, pie charts. There is a large variety of different graph types that you can choose, as well as tables, and these can be exported to Excel, or the figures can be exported to PowerPoint. Under energy balance, you can see the calculated energy results as specifically formatted in the form of energy balance tables and Sankey diagrams. Under summaries, you can create your own customized tabular reports, including cost-benefit summary reports, MAC charts, and decomposition analyses. Under overviews, you can find your favorite charts, which you can create in the results view and save this way. This allows you to easily come back to charts that you've previously created and look at them with new results. The technology database provides the default data on the technical characteristics, costs, and environmental impacts of various energy technologies that are available internationally and in particular regions. And these are predefined in LEAP, and so they're very easy. It's very easy to access this database. And then finally, there is the notes view, which is a simple word processing tool where you can enter documentation. This is here on the bottom. And it opens up this window, and I just want to really encourage you to document your model in as much detail as possible as you go along. This is really useful as you continue model development, or as you share your model with others. It really allows you to keep track of the data that you add and the assumptions that you make, and is extremely important. So the user interface of Leap, it has, as I mentioned before, and as you've seen just now, this graphical user interface. The main menu, which you can find on the top, provides access to the major options. And then the data are organized in a tree. And the available variables depend on which part of the tree you've selected. So you can select the highest level and it will allow you to see kind of the overview. But as you want to look at specific variables, you'll have to go into the tree, and then the different variables will show up here on the right. And you can choose between the different input variables that are available for the specific point in the tree that you're at. Just going to go into demand in this Fredonia model in the analysis view. So here you can see the different variables on the right. So when we go into activity levels, this is where you would add your data, and which is what we call expression. So this is very similar to a formula that you would enter into a spreadsheet. And generally, all expressions that are added here in Leap are time series. So they cover multitudes, all the years that you are trying to project into the future. You can edit data and expressions here, and you can change their units. Leap has a variety of units available, and they will convert and it will convert your units automatically. So you don't have to add all your data in the same unit. If you need more room to add expressions, you can use the Builder tab. So here, this is the Builder tab. I'm just going to switch between Nodes and Builder so you see the difference. This is exactly the same, has the same input as the expression up on top, but it gives you much more space to add a formula. And then every variable also has this Nodes tab. And as I said before, we really encourage you to make use of this. It's a simple text editor. You can just add notes, and they will live with the model and be shared. If you share the model, the notes will be in that model already, and you don't need to reference a separate documentation manual. So really, we encourage you to make use of this Notes tab. Once you add data,
Charlotte,
you can look at. Mm-hmm.
I'm sorry to interrupt you, but a question has just come up, which I think would be worth just addressing in plenary right now. And the question, Jindan Gong asks, what is the 2010 value that's shown in the table or the grid in the top right part of the screen? And is that a fixed value, or can it be adjusted in the model? Do you want to speak to that for a second?
Yes, of course. Well, thank you for that question. I think that's a very useful question. So the 2010 value in this case is the historical value. So this is a value that we actually have data on. And it is added under what we call current accounts, which is the historical, which covers the historical part of the model. And yes, that can be evaluated. Here in this particular case, we're in the reference scenario, so we're only changing values for future projections, but you can add, you will be changing values in the current account. Is there anything you would like to add to that, Jason?
Oh, no, just to note that is the last year of historical data in this particular model. So if you had a different set of historical data, then it would show you a different last year value there. And it's just for reference as you're developing projection scenarios. which are scenarios that look into the future just so you can see what the last historical value was, but it can be changed. Thanks, Charlotte. Go ahead.
Great. Then the next, so now we just looked at the analysis view. So the next tab on Leap is the results view. And if you haven't yet calculated results, once you click on results, it will calculate the results of the current model setup for you. Results, similar to the data in analysis view, can be shown as charts, tables, or in the map format if you have that capability turned on. And in the way that these charts work is that on top, you select the output variable here. So in this case, deaths. You can set other context-specific options on the very top level, like you can increase the number of levels, which is essentially how deep you look into this data tree. You can define chart series here. You can look at different branches, pollutants, fuels, years, and scenarios. You can define which type of chart you would like to display. You have pie charts. You can display the data as bar charts. There are area charts. So there's a variety of different ways that you can visualize the data in. So here we're showing death and comparing the baseline scenario to a national action plan in red. And you can export these outputs directly to Excel or PowerPoint. If you export them to Excel, it will export the table, which you can also look at here if you click on the table tab. I'm not sure. Yes. So I'm not going to look at the diagnostic messages. So this will just recalculate. So here, this way you can switch between the table and the chart view. And you can export these figures directly to PowerPoint as well. On the bottom, you can define a chart's x-axis. You can usually select the branches, pollutants, fuels, scenarios, years, and more, depending on what you have set up in your model. And the data shown and available output options depend on your location in the tree. Again, similar to analysis view, where you can only see the variables of the specific point you're in the tree. Also here, you can only display those results that are underneath the specific location that you're in the tree. So if you are not finding a variable that you would like to look at, it may just be that you're not in the right location in the tree, and you should play around with selecting a different location here. Something that I would just like to add as a general indication is that you can always see the version of Leap that you're running here on the bottom left. I'm running version 48, which will probably be what you have installed. We encourage you to update your versions regularly. Leap will alert you to new versions that are being released. And you can choose to update or not. It will also tell you what is included in a new version. And the other things it tells you here at the bottom is what area. So this is what Leap refers to when it's Leap's terminology for a model. It's the area. This is the model for Fredonia. It tells you what view you're in, results, and then finally it tells you who this particular version is registered to, in this case, me. So that is just whenever you are trying to verify what version you're running, this is where you'd find that information. So then let's talk a little bit more about the tree. I've already mentioned it a few times. The tree is in Leap defines a modeled structure. It organizes input data and results, and it's made up of branches, where each branch contains context-dependent variables. The top level of the branches is set up automatically by Leap depending on what settings you set when you create a new area. But the sublevels of the branches are generally determined by the user. And the tree in Leap supports standard graphical user interface interactions. You can move around branches by clicking and dragging, and you can copy and paste. And so creating a tree using that and reorganizing it is really made very easy. There are different types of tree branches. The higher levels are the categories, which are these little folder icons. They're used mainly for organizing other branches. You then have also other icons. We have icons for technologies, which can look like this. They're referring to final energy consuming devices and energy transformation processes. And you can see them here on the left. So for example, this little wheel indicates a new oil combustion turbine. So this is a technology. And then you also have key assumptions, which are LEAP terminology for user-defined independent variables. So these are, for example, the demographic and macroeconomic variables, and they're defined under key assumptions, which is the highest level in a LEAP tree. And then you also have icons for fuels. There's a large variety database of different fuels included in LEAP, which you can access. And then when you add them to your tree, they'll be indicated, like here, coal bituminous as a fuel. And then finally, we have little cloud icons for effects, and that's just LEAP terminology for different pollutants or environmental loadings. So in this particular branch that you can see here on the left, 7 different pollutants were included for coal bituminous. You have carbon dioxide, as well as methane, non-methane volatile organic compounds, NOx, nitrous oxides, and sulfur dioxides. And there are many more included in LEAP that you could quantify if you were so inclined. LEAP's modeling methods essentially are comprised of 2 levels. Basic non-controversial physical accounting calculations are handled internally within LEAP. They're used to account for energy, equipment stocks, natural resources, costs, and pollutants. And then users can also, at a second level, specify additional modeling for LEAP expressions and other options. Expressions, as I said earlier, are similar to formulas in spreadsheets, so they're used to specify the values of variables. All expressions in LEAP define a time series that cover the full horizon of your scenario projection, so going from the last historical year, which in this case, as we just said earlier, is the 2010 value, all the way into the future to your final projection year. The time series can be constant in all years, so you could have the same value for each year going into the future, but you can also have a time series that changes through time. And there are many built-in functions in LEAP that can be used for that, and you can also refer to values of other variables. And so just to illustrate that, when you go, let's go back into households. So as we're looking here, this essentially says that the 2010 value will grow at 3% a year over the projection time series. And so you can enter a different expression here. You could just enter a single value. You could also refer to another variable, and you can simply, you could simply drag variables into this, but you can also search for them through this branch and variable search wizard. And so you can add variables to your expressions this way if you would like to refer to, for example, to a key expression like income. It's not letting me do this right now. But you can simply drag and drop variables from the branch here as well. All your expressions can also be linked to Excel spreadsheets. So if you have your data in Excel, rather than adding it manually, you can also link it directly to a spreadsheet. And there is a function in Leap that allows you to read directly from Excel. And you can inherit variables from other scenarios and regions. You don't have to redefine every variable in every new scenario that you're developing. Some examples for expressions are shown here. So as I said, they could be a single constant value in all scenarios, or they could follow a simple formula. So for example, you could have, in this case, 0.1 times 5,970 would yield a constant value of 597 in all scenario years. You can have a growth rate, which is what we just saw, the example of growth of 3.2% annually, which calculates an exponential growth over time, as you can see here on the right. You can interpolate between values for different years that you would like to add. So in this case, you're adding values for the year 2000, 2010, and 2020. And Leap will perform the linear interpolation between values for you. You can add data as a step function. This will increase or decrease to the new value at the time point that you've set in this function. And you can also have a variable grow in the same way as another variable. So in this particular case, you're defining that you want the variable to grow like income. And this causes the variable to grow this causes the income variable to grow at the same rate as another variable, in this case, elasticity. I'm not defining this right. Let me correct. This causes this variable to grow at the same rate as income, subject to a specific elasticity. Ways to edit expressions. In analysis view, you can, as I just showed you, directly edit an expression above. You can go into the expression builder below using the function wizard. You can select branches and variables from the branch variable wizard, and you can also use the time series wizard to enter time series functions and data. And there are multiple ways to import and export data from into Excel. Let me just show you one important function. So for one, on the right-hand side, now that I added growth here, you can see the syntax for growth. So this will there will be a little help menu on the right where you can look up the syntax of a specific function. There's a description of how the function works, as well as some examples. So this is very helpful. And you can also go to the help tab, and this will open the Leap documentation. And so here under expressions, you can see all the expressions that are available in Leap, and you can look at their documentation. And this will also be very useful in setting your own expressions in Leap. Leap is an extremely powerful tool to carry out scenario analysis. The future is, of course, unknown, but we can explore it using scenarios. What do we mean by exploring it using scenarios? We can look at internally coherent and physically plausible storylines that describe a possible state of the world in the future. So we can explore what different pathways in the future may look like. In LEAP, scenarios are represented by exogenous inputs, calculation methods, and results from the inputs and methods. LEAP recognizes two types of scenarios. One is the current account, which contains the historical data. So this is data that is known and that would be added a priori. And then it also has future projections, and this includes the baseline, so a scenario by which you essentially presume that a world which maintains the status quo and policies are decided upon in accordance with current preferences. But then you may also be looking at different alternative policies, mitigation measures, and similar changes to the baseline, and explore what the impact of these changes is on total energy demand. You may be looking at total greenhouse gas emissions. And so LEAP is really developed in order to allow you to do that. Scenarios in LEAP can inherit expressions and data from multiple other scenarios. So here on the left, we have a scenario called DP30, Decarbonization Pathway 2030. And that scenario is based on the baseline, but it includes a variety of what we always often call mini scenarios. So individual measures that are focused at a specific sector, for example. So, for example, it includes gas leakage reduction, decarbonized electricity supply by 2030, a forestry sink. It includes decarbonized transport, and all of these scenarios, these mini scenarios, are included in this greater scenario called the Decarbonization Pathway 2030. It is really important when you add scenarios, what order you add them. When you add these mini scenarios, what order you add them to the overall scenario, because LEAP will follow this order when searching for expression and data to inherit. So if a specific variable is not defined in the topmost scenario, LEAP will go and search the next scenario that has been included, and look for the variable there, all the way down to the baseline. And if none of these variables has been defined in any of the future projections, then the last scenario in the inheritance chain is always current accounts. So if it will just go with the values that are defined in current accounts if you haven't defined any values for this variable in any of the upper scenarios. Something else to note is that expressions are color-coded in the analysis view, and blue means that this particular expression was defined in this scenario. Black means that it was inherited from another scenario, and green, which is not shown here, means it's inherited from another region. So merely by looking at the expression, you will also be able to tell whether this is something that has been changed in this particular scenario, or whether it's something that is merely inherited. LEAP provides powerful features for analyzing and comparing scenario results. You can look at the differences between scenarios, which is what we looked at earlier in the bar chart, where you saw the two bars side by side. You can look at the amounts avoided in a scenario, which is what is shown here on the right. The white area refers to the 100-year GWP avoided versus the baseline, in this scenario versus the baseline. And you can look at scenarios in a series of charts or tables, so you could create individual charts and tables for each scenario. Something that we always like to show is this LEAP glossary. It's just a helpful tool to understand some of the words we use as we talk about LEAP. Some of them you may already have heard me use now, but I'm just going to go through them again to make it really clear. So an area in LEAP is a LEAP model or a system being modeled. Areas may be divided into multiple geographic regions in LEAP, but when we say area, we refer to a specific LEAP model. The base year is the first year in a model, and the end year is the last year in a model. A scenario is a consistent set of model inputs and results corresponding to a possible state of the world. A model can contain multiple scenarios, and most commonly does contain multiple scenarios because it's usually used to explore different alternative pathways. When we talk about current accounts, we refer to a special scenario that contains the historical data. Every model has a current account. It's the start for the future projection scenarios. The first scenario year is the year following the last year in current accounts, and the first year in projection scenarios. So as we saw earlier in this little expression chart, 2010 is the last year in current accounts. So the first scenario year would be 2011 in this case. The tree is the hierarchical data structure that organizes a model inputs and results, and it can be seen on the left in analysis view as well as in the results view. And the branch is an item in the tree, a category, a technology, so it's a sub-level in the tree. And includes also the key assumptions. Variables are there are input variables for models which are contained in the branch, and then branches may have multiple variables which are shown in tabs on the screen. And finally, expressions, I think those that we already talked plenty about, but it's a formula that specifies a time series of values for a variable in a given branch, scenario, and region. So we talked a lot about what LEAP is, but there are also some things that LEAP is not. LEAP is not a system dynamics model. It's not a general equilibrium model. It's not a macroeconomic model, and it's not an agent-based model. It's not an electricity system production cost model or an electricity system network reliability model. These are not things that LEAP is used for, and so, or the things that these models are used for is not something LEAP is useful for. We have a variety of examples of LEAP applications, and so I just wanted to show some that may be most relevant to the audience today. LEAP was used in the 6th Asian Energy Outlook, which was a regional LEAP model with national detail. We modeled energy demand, energy supply, and emissions using bottom-up modeling of key demand and supply sectors across all the countries included in the ASEAN region. And it was used to simulate national plans and policies and regional targets, including the attainment of the Sustainable Development Goal 7. Another example of a LEAP application was the Integrated Resource and Resilience Planning in Lao PDR. This was a project where we partnered with the USAID Clean Power Asia program, the Ministry of Energy and Mines in Lao PDR, as well as the electric utility in Lao PDR. And for this project, we developed a highly resolved LEAP NEMO. NEMO is the optimization tool within LEAP. A highly resolved LEAP NEMO model of the national electricity model, including power flow modeling, and it was applied in a large scenario ensemble analysis in order to allow robust decision making. So decisions that are robust to a variety of possible futures.